in November, okay? Yeah, when it comes to December, I will do that, okay? I will upload the sample final, okay, which will be like the final used for in the last year, okay, to the E class, okay? So, okay, so come back to the class, okay? So, over these years, okay, there are so many important architectures being developed, okay, which leads to like like advancement in like image or like vision research, okay, among different like platform, okay. One of the most important platform is called ILSVRC Imagenet Challenge. Okay, this ILSVRC is actually a conference abbreviation of a conference name. Okay, C stands for the conference, but I forgot like the full name of this conference. But anyway, the most important thing in this conference is that they prepare a data set, okay, called the Imagenet data set, okay, and they require, this is a challenge. I mean, they ask like everyone interested in competition, okay, to provide their model, okay, to recognize, to classify, their test data set, okay. So how big is this test data set? Okay, the image data set is each image is a large image. Okay, when we say large, okay, it's 256 pixel high. Okay, so we are not talking about 28 by 28, the tiny like fashion MNIST data set. Even though by the current standard, okay, because we are in 2022, year 2022. So when you see, the pixel height is 256 only, you say this is nothing, right? This is nothing. But this competition start from, I believe it's like 2012, about 10 years ago. Okay, I'm not saying 10 years ago 256 pixel height is large. No, it's still not large, but it's at least it's a reasonable size image, okay, for competition, okay. And there are 1,000 classes, okay. Back to 2012, this is a very difficult vision challenge to classify 1,000 classes, okay. So some of which are really difficult to classify. For example, okay, in these 1,000 classes, there are 120 dog breeds. I know some of you are dog lovers, right? So you probably know like poodles, like Chihuahua, okay? But when it comes to 120 breeds, that's a lot, right? Some dogs, I don't know, like are very difficult to tell their difference, right? I mean, I'm not saying like if it's poodle and Chihuahua, obviously you can tell poodle from Chihuahua. I mean, obviously that's not difficult. But if it's some, well, I probably cannot give you like exact like dog breeds that are similar. But you get an idea, okay? I mean, same thing goes for cats, right? Some cats they look similar, right? Even though they belong to different breeds, but they just look similar, okay? It's difficult. The difference is just very tiny, okay? So okay, so this is very difficult task. So of course we are not talking about exact like 100% accuracy here because it's just too difficult. 1,000 classes come on, it's just too difficult. But okay, they use what we call top 5 error rate. Okay, what is top 5 error rate? That means, okay, you are allowed to guess 5 times. Okay, so you can, for example, you provide your answer. Okay, the most likely 5 classes for this picture. Okay, so if your top 5 answer, one of the top 5 answers is correct, then it is considered correct. Okay, that's what we call top 5 error rate. So of course, if all the 5 answers are wrong, then it's considered incorrect. That's considered error. Okay, so originally, okay, in 2012, okay, the champion, okay, the error rate is 26%. Well, if it's a human to do that, okay, assuming you know dog breeds and all those tiny details of those 1,000 classes, you should be able to do better job than 26% top 5 error rate. Okay, for human, okay, we can pretty much beat them, okay, beat the model. But it quickly, okay, after a couple of years, just 6 years, okay, this competition, by the way, is no longer there, okay, because it's considered too simple nowadays. Okay, so yeah, this is a famous image classification challenge, but currently this competition is no longer there because it's you see the top 5 error rate is reduced to 2.3%. Okay, in 6 years, so it's about 2018. Okay, it's 2.3%. Is crazy, for a human. Okay, if you are able to have maybe lower than 5% top 5 error rate, that's already very good. So this 2.3% top 5 error rate obviously is much better than a skillful human. Okay, so this is we are going to review some of the famous models introduced, okay, in this competition, okay, especially those models who won the champions, okay, and some of the ideas in those models are worth considering, okay. So we'll first look at the classical LaNet 5. Remember, I told you this LaNet 5 architecture is widely considered to be the first CNN architecture, which was proposed in 1998 by Yang Chong. Okay, but this is not for this image Imagenet challenge. Okay, but because this is the first CNN architecture, so it's also worth mentioning. Okay, just for the historical reason. Okay, and then we are going to talk about the winners of these challenges, including AlexNet, GoogleNet, ResNet, and some other as well. Okay, I didn't list it here, but we are going to talk about that. Okay, so the first one is LaNet 5. Okay, so LaNet 5 architecture, okay, is the most widely known CNN architecture. Okay, it was created by Yang Chong, 1998. So it's used to recognize handwritten digits. Okay, the data set is called MNIST, not fashion MNIST, but MNIST. But the MNIST is considered simpler than fashion MNIST. Okay, so it's composed of the layers. Shown in this table. So there are several observations that we can derive from this. Okay, first, okay, well, remember the MNIST data set. What is the size? You guys still remember, right? 28 by 28, right? Okay, we talk about facial MNIST, but you know, facial MNIST gets the name MNIST because it has the same size, okay, and the same, a lot of similar, like 10 classes, a lot of similar property to the MNIST data set, okay. So yeah, you know the size of the image is 28 by 28, but you say, wait a moment, the input is 32 by 32, it's not 28 by 28, right? Okay, so the input actually will be stretched, resized into 32 by 32 before it is fed into this model. Okay, so this model, let me first tell you, okay, this model, we mentioned this model, it's not because this model is the state of the art. Okay, this is, as I say, it's for the historical reason. Nowadays, as I already show you, like we can use like a lot of, even the MLP model to deal with MNIST data set. Okay, and obviously we can create a traditional CNN model which does not require we to stretch the input image, right? So I mean, but at that time, okay, this is the model they use, okay, and then okay, you can see what is the, you know, the activation function they use. Hypertangent, okay. This is back to 1998, okay, 24 years ago, okay, almost a quarter of the century ago, right? So at that time, they still consider, you know, to use hypertangent, okay, as an activation function, okay. But nowadays, as I said, okay, we a lot of time avoid using hypertangent. We normally use ReLU, right? Let me make it clear. Okay, we still use hypertangent at some particular models. For example, like later on when we talk about RNN model, okay, then you will see hypertangent being used more often in that model because that's a special case. But for the other situations, we don't use hypertangent that much anymore. Okay, and you can see the kernel size. Okay, well, it's we have 6 maps, and the kernel size. This is the map size. Okay, map size. The kernel is 5 by 5. Okay, it's, you know, the first one is large, but you can see we also have a large kernel for the second convolutional layer. Okay, that's very special. Well, and the third convolutional layer is also 5 by 5. At that time, I mean, they do not know like the advantage of the small kernel. Okay, and also, okay, even though we now know, okay, well, we should, I mean, some of the architecture that we are using now, okay, I mean, has been here already. For example, you can see the number of feature map increase more and more. We have more and more feature maps, right? And the size of the feature maps, well, is reduced, right? And to like 1 by 1, and then which is connected to one fully connected layer, and then this is output layer. So you can see that the basic architecture of the CNN can be found here. So that is why this is considered like the first CNN model. Okay, but there are some differences. There are also some similarities. Okay, but I have to mention, for example, okay. For example, some of the layers are not exactly like what we use now. For example, the average pooling layer, okay, yeah, they also use average pooling. They don't use max pooling like we do more often nowadays. Okay, but their average pooling is also different. okay, each neuron computes the mean of its input, and then multiply the result by a learnable coefficient, okay, and adds a learnable bias term. So it's kind of like it is doing like what should I say, like sort of like a normalization, okay. Although they are not dividing the batch like average or and do like shifting to 0, okay, but you get idea, okay. So this is like kind of different from the average pooling that we are talking about now, okay, nowadays. And also, you see, most neurons in C3 maps, C3 is the convolutional layer, the third convolutional layer, okay. The third layer, which is convolutional layer, okay. So are connected to neurons in only 3 or 4 S2 maps instead of all 6 S2 maps. So you see, there are some strange tweaks, or I should say, small strange tweaks, okay, in this model, which are not standard. When you compare it with like the current CNN, but if you want to see like the detail, how they connect this, do these connections, you need to refer to their original paper, okay, 1998 paper, okay. In the table 1, they have the detail of those, okay. And output layer is also spatial, okay, because nowadays we use softmax, right? We use softmax for classification. At that time, they don't know that. Okay. So they didn't know softmax. So they use dot product of the inputs and the weight vector and so on. So they use some strange like approach. Okay. They do each neuron output the square of the Euclidean distance between its input vector and its weight vector. So you see, this is very different from softmax, right? So each output will measure how much the image belongs to a particular digit class. So now that we use closed entropy, because closed entropy actually provide more gradient for us to train the model, okay, better. But the way they use, and back to like 1998, is no longer a good approach. But just for historical reason, I just want to bring this up to you, okay? And Yang Lechong's website also has a LaNet section, okay, feature a very good demonstration of LaNet 5 classification. Let me show you, okay, where is it? Here. Let me use, do I have the internet connection? No, I don't have. One moment. Okay. Click on this again. Here. Okay. I hate this. Wow. It doesn't, because this slide is still here, so it doesn't show the. Let me. Okay. Okay. Let me move this. Okay. So this is Yang Lechong. Okay. The one that I want to tell you is here. You see, he has several achievements that he thinks he's that is worth mentioning in his career. So what is the .NET? Okay, so if you click on this, it shows you, so this is the .NET 5 network architecture, okay, and it shows you when an image comes in, okay, what does each neuron see the image, okay, in a visualization, in a visualized like a manner, okay. So it is very interesting. I'm sorry, it's the other way around. From here to here, it's layer 1, layer 2, layer 3, layer 5, okay. So it's this way, the other way around, like here. So you guys know like there's like a famous research field called explainable AI. Okay, because the deep learning is always considered as like a black art, right? Because you just feel like, oh, you put stuff into it and it will spit out the result to you. Okay, but you don't know how it does the job, right? So here is a visualized, explanation of the process, how the digits gets recognized. So which is kind of interesting, okay? And you can see it's quite accurate. It's quite accurate. Okay, so yeah, so that's let me. Okay. So if you are interested, you can go to Yang Lechong's website. Okay, I believe he doesn't spend too much time as a professor at NYU now. Okay, because he's the head of the Facebook AI lab. Okay, which is called FAIR, by the way. But you guys know how Facebook is currently doing, right? I mean, yeah, they lay off like more than 10,000 employees. I mean, I don't think, Yang Lechong will be laid off, okay? If he got laid off, I think he can find a job like anywhere easily. I mean, from Google, from Microsoft, from those big companies so easily, okay? But, just want you to understand that, okay? He probably doesn't spend as much time in his academic job as previously because the industry competition is very strong now. Okay, but anyway, if any of you is considering like studying abroad, okay, NYU is still a good place to go. Okay, I have a student who went to study under Yang Lechong. Okay, many years ago. Okay, so anyway, so that's the .NET 5. Okay, and just want to give you an idea. Okay, of the first CNN architecture. Okay, in the world. Okay, so then, okay, as I said, okay, the Imagenet Competition is a famous platform. Okay, which allows like the state-of-the-art development of CNN researchers to showcase their architecture. Okay, so the first model the model that won the first challenge in 2012, okay, is called AlexNet. Okay, so its top 5 error rate is 26%, and it won by a large margin. Oh, sorry, it achieved 70%. The second best achieved only 26%. So you can see the difference is 9%. So it's a huge difference. Okay, and it was developed by Alex, okay, Ilya, and the third name is actually more famous, Jeffrey Hinton. Okay, but this model is named after the first guy, which is, I believe, is Jeffrey Hinton's student. Okay, the first two should be his student. Okay, so you can see this architecture is similar to LANet 5, but much larger and deeper. Okay, so it is also the first CNN model to stack convolutional layers together. Okay, before that, before this model was introduced, everybody just put in one convolutional layer and one pooling layer, and one convolutional layer, one pooling layer. But you can see now, okay, in this one, okay, you can see we use like for example, here we have convolutional layer followed by a convolutional layer, and the third convolutional layer. So we have three convolutional layers stacking up together. Okay, so let's first observe this architecture. Few things to note, okay, is that, okay, first, the kernel size is huge. So it's 1111, right? So it's a huge kernel size. At that time, they already know we could use large kernel size for the first convolutional layer, but not the other one. Okay, for the other convolutional layer, they use much smaller kernel size, right? Even though we think like 11 by 11 is too big. Okay, if we consider this using the standard, today we think it is really too big, but still, okay, they get the idea. Okay, they can use large kernel size only for the first convolutional layer right after the input layer, which is correct. And also, as for like you see the feature map, size gets reduced. Okay, and and the number of feature map gets increased. These are just like even it's just like the LANet 5. And one most important thing is you can see at this moment, in 2012, okay, they already switched from the hypertangent to ReRU, right? Back to 1998, okay, 16 years ago, okay, 14 years ago, sorry, 14 years ago, they still use hypertangent, but now this one actually looks quite fashion already. And also they use max pooling. They don't use average pooling anymore, right? And which is the result is followed by fully connected layer. Okay, so this is sort of like a fashion, kind of similar to a fashion model. Okay, so in this AlexNet model, okay, they use two particular techniques. Okay, one is called where is it? Okay. Yeah, they use dropout. We talked about dropout previously, and they perform data augmentation. The dropout, we talked about this already. So they use dropout in F8 and F9. Okay, so dropout is used here, but they didn't. The table didn't show here, but the dropout are here. But well, as I said, we usually use dropout in a fully connected layer. Okay, but the second one, the augmentation, data augmentation. What is data augmentation? Okay, data augmentation is like you randomly shifting the training image by various offsets, or flipping them horizontally, changing the lighting conditions. So if it's the same thing, okay, if it's the same thing, you try to same object, you try to change the angle, you try to change the light condition, or like flipping the image object horizontally. Normally it doesn't change the type of object, right? But the model normally will consider the input as a different input. Okay, so in some sense, okay, you enlarge the training data size, okay, without really collecting more data. And also, this data augmentations idea actually help like the model to be more resilient to the small change of the image. Okay, so even like this data augmentation concept has been used a lot. Okay, even like the current famous model, such as, for example, some of you who are a little bit into the vision research should heard about a model called YOLO, right? Okay, YOLO, when YOLO is trained, they use data augmentation as well. Okay, so this is an important technique. Okay, let me show you a picture. Okay, so this is a mushroom. Okay, it's already labeled. Okay, and here you can see we change the angle a little bit, right? And this one we just try to move the area that we crop the image. Okay, we move a little bit to the right. Okay, we change the angle, move the area to the right. We make the lighting darker. Okay, and here we enlarge the image. This one we actually shrink the image a little bit, and here we just try to make the lighting, increase the lighting. Okay, but you can see obviously this represents the same mushroom, right? And I mean some augmentation also, flip the image. So if this is the mushroom, okay, obviously if you flip this image horizontally, it will be the same mushroom, right? Okay, but a lot of, the data augmentation, okay, also provide like a option that allows you to flip the image vertically. Sometimes it works. Okay, for some image. Okay, for example, like what should I say? Okay, if it's like there are some objects that if you flip it vertically, it will be the same thing. But for some other object, if you flip vertically, it's probably not a good idea. For example, let me use this mushroom as an example. If you flip it vertically, well, you can say, oh, it's still a mushroom, right? But you normally don't see a mushroom grow like like that, right? So for example, like one of my students, he's doing like research on object recognition. He's trying to recognize like a speeding limit sign. Okay, the speeding limit sign. Normally, if you drive or ride boat motorcycle on the road, you see like there are speeding limit sign on the road or like on the post, right? So for those speeding limit sign, you cannot even flip it vertically or horizontally. Even horizontally is not possible. Why? Because, for example, if it's speeding limit is 60, if you flip it horizontally, it will become, right? There's no such speed limit, right? Okay, you don't see a speed limit like that. So if it's number, if you flip it horizontally, it doesn't work. Not to mention you flip it horizontally. Okay, so the data augmentation. Normally they provide like an API that allows you to use them to create those augmented features like automatically, okay, during training, okay. But there are some options you need to be careful when you select them. For example, like this flipping, whether or not your application is suitable for vertical flipping or horizontal flipping, it depends on your application. Okay, just want to understand, okay, this augmentation concept. Okay, so so I think I already explained that. So the other there's also another interesting concept brought up by Imagenet, okay, which is called local response normalization. Okay, so this local response normalization is a technique that what should I say? Like the purpose is to make sure, okay, the feature maps, okay, the consecutive feature maps should pick different features as much as possible. Okay, so how do they do that? Okay, basically they use this one. Okay, basically the AI is like the original output, okay, the activation of the neuron after the reload step, before the normalization. And here is K plus alpha, this AJ square, okay, this AJ square, the sum of AJ square is actually like, you are trying to collect like, what should I say, like this is like a, for example, do I have a picture? No picture. Okay. Anyway, so so if this is like a particular point in a feature map, okay, they will try to calculate, okay, its neighboring feature maps, the same location. So the top one says here, lower one says here. Okay, well, I'm a poor drawer. Okay, just bear with me. Okay, so for example, so if this value is AI, okay, and the top one and the lower one, this is AJ, this is AJ, okay, and it will have this R, which control like how many neighboring feature map you want to control. Okay, so basically this is AJ, this is AI, this is AI. So basically they just collect all this AJ and square of all these AJs, add them up. Okay, multiply alpha and the plus a K, and they want to bound the whole thing, okay, by BI. Okay, so you can imagine if this AJ, some of these AJs have a larger value, then it will affect this AI, right? It will force this AI to have a smaller value, right? Because the whole, this whole value, the whole result is bounded by a number. Okay, so if these values, any of these values is huge, then it means like pretty much that the feature for that activation feature map at that particular point is activated, right? So we don't want this area, this one, okay, which is happen to be the same location to activate. We want to force it to learn something else. Okay, so we try to use this formula to constrain the output of this output value of this location. Okay, so basically, okay. So for example, if I is 2, I is 2 means like we only consider the immediate top and the immediate lower feature maps. Okay, if a neuron has strong activation, it will inhibit the activation of the neuron located in the feature maps immediately above and below its own. Okay, so there are some hyperparameters. Selected here, but I will not go into the detail of this. But so this is the winner of because of the data augmentation, because of this local local response normalization concept. Okay, this Imagenet won the 2012 competition, and a variant of Imagenet called ZFnet, okay, which was developed by Matthew Zayler and Rob Fergus, okay, because they're the initial of their last name, okay, happened to be ZF, okay, so they call this as ZFnet, okay. The ZFnet won the 2013 challenge, okay. Basically, it's the same as Imagenet with some tweak hyperparameters. So basically, like not too much to talk about for this particular ZFnet model, okay. So which means we will move to the 2014 winner. But yeah, let's take 10 minutes break. When we come back, we will discuss this Google Net. Obviously, you can tell by the name. This is proposed by Google, right? Okay, and also the reason they have this name is to pay respect to LaNet 5. Okay, so that's why they got the Google Net. Okay, so we'll talk about this in 10 minutes. Okay, let's take 10 minutes break.